And then I go back to today's text channel. So try to use the text channel or use voice to ask questions. And I can hear both Discord and also Google Meet at the same time, so you can use either one to talk back to me if you have any questions to ask using voice. If you want to type, then the only channel I'm watching is Discord. So if anyone is typing over at on the Meet side, I'm not going to be able to see it because that window is completely covered. I can't see it. All right. So yes, so for those who are on the wait list, if you have not received a permission number from me, and if you have received the permission number from me but you haven't used it, it's too late to add it using just a permission number, but you can still add. So the idea is to Google search for what we call a late add permission form. So I'm going to search that for you guys too over here. So you just type in Lowe's. Well, you can type in this American River College late add petition. Okay, so it's a petition form. The first link is the correct one. Just kind of click on it. It would say that you need to personally, carry it and hand it to the division office people. That is not required anymore. Okay, so you want to send it to the division secretary. His name is Kevin. Kevin last name is Xiong. So you want to send him that form, a field form. Send it to Kevin. And then proceed from there. I just got one today. I'm not even sure whether it's from this class or not, but I just got one today, and it's got to be completely online. I don't think you have to be physically on campus to turn in the form. That just doesn't make sense anymore. All right, so we got
Keaton, you're on open mic.
3 people coming in. All right, there we go. All right. I do not know whether this is going to be going through e-services. I just know where we can download the form. So once you get the form, you send it by email to Kevin. And Kevin's email, I'm going to post it in the text channel. So his email is xiongk@arc.lowesrios.edu is the person to send the petition form to. Okay. There we go. We got 2 people typing questions, and then we'll get the class started because we are 2 minutes past the time. Okay. Now Discord just says, several people are typing. Very good. Very interesting. I've never seen that before. Okay, so there's a way to use e-services to get the form. Okay. Yeah, maybe. So our home base person who is Lily, she may be able to get you to join the design hub, but ultimately it is, Schuster who's gonna sign off the form and say yes, go ahead, and they would want you to sign up for I think it's design for 98 units, so you would need to basically sign up for those units too. So we'll talk about that maybe after class, because we got like 3 hours of lab time, after class to talk about that. So we got plenty of time there. All right, so we are gonna go back and talk about binary addition. Okay, so base 2. Okay, we are just talking about base 2 addition, and we'll go ahead and look at my tablet. I found the stylus, so this time I can use it again. All right, so we'll go back and kind of talk about base 10 operations first, because we should be fairly comfortable with base 10 multi-digit addition at this point anyway, right? Because we are in computer science, and computer science is really a discipline of math. I mean, people don't want to think about it that way, but that's basically what it is. All right, so we'll talk about multi-digit addition. So I'm going to use a concrete example to start with, and then we'll get to the structure, okay, and then we'll translate the structure into base 2. Okay, so it's a three-step process to get back to base 2 addition. So we'll start with a base 10 example, 982 plus 219. Okay, so that's, I just randomly picked some number that I thought will illustrate all the points that I need to illustrate. And I'm going to start to label the rows. This is X, this is Y, and then this one is called Q, this one is called K for carry, and then this one is S for sum. Okay, so X and Y are the original values or the numbers that we're trying to add. Q is kind of interesting because it's a quote-unquote partial sum. Okay, and then K is the carry from a less significant digit, and then S is for sum. That is the actual answer that we want. Okay. So the way we do this is to figure out what is X plus Y. So the way I'm going to do this is going to be very kind of interesting, because the first thing is to define what is Q. Okay, Q by definition is really the result or the single digit result of adding two digits, X and Y. Okay, so Q of I is the result of adding Xi and Yi as single digits. And in this case, the I is a digit position, so I is 0 oriented. Okay, so we have x0 being the 2 and the 9. X0 is 2, Y0 is a 9, and so on. Okay, so Qi is really the R, the single digit result of adding Xi, Yi. So we got a 1 here, we got a 9 here, and then we got a 1 here. Okay, you look at this and go like, but then what about the carries, right? So the carries are going to be in the K row. This one is a 0. It is assumed. Okay, it is usually assumed to be a 0, but as we will see later on, okay, sometimes it's helpful not to assume that that is going to be a 0. Okay, so for now we're going to say we'll just assume that there are no carry to digit 0. Okay, so now we try to define what the k's would look like. So ki plus 1 is going to relate to two different terms. So the first one is the carry of adding xi, yi. Remember xi, yi are single digits. And then the second component is the carry of qi, ki. Okay? And the question is, how do we relate these two? Okay, so that part I haven't talked about yet, but we'll get to see how that is important. So we get back to the example first. 2 plus 9 is, well, we know it's 11, which is also known as a 1 with a carry of 1. Okay, and then 1 plus 0 is a 1 over here. And then what we will do is to do the same thing for the for digit 1. So we got 8 plus 1 is a 9. That itself does not give us a carry of 1. But then 9 plus 1 does. Okay, 9 plus 1 will give us a 0 and a carry of 1. And then we have 9 plus 2 being 11. So it has a single digit result of a 1 and a carry of 1 as well over here. And then 1 plus 1 is a 2. And then this carry, this overall carry, is not really represented as part of the sum. And that's because we want the sum to have exactly the same width as the numbers that we are adding. So in this case, the values the numbers that we are adding are 3-digit wide, and as a result, the sum is also only 3-digit wide. And yes, we do end up with an overall carry of a 1 that is not considered a part of the sum. Okay, so I want to go back to Alex's question. You need to turn in the late add form to I'm not sure whether you send it to me first. I think you should send it to the division office first, and they will forward that to me. Okay. As long as I have proof that you have been attending classes since the beginning, I will sign it off. It's not a problem. All right. So now we want to focus on the part where, hey, this is the reason why we have that one over here, but this is the reason why we have this one over here, and then this is the reason why we have this one over here. So now the question is, what is a good way to summarize, right? How we end up with a 1 on the next column, okay? The column next to the one that we are dealing with. And that's because that's why we have a ki plus 1 over here instead of just, k of I. So the first thing we instinctively do is to say, we'll just do an addition, okay? This plus does not mean or. It really means an addition, okay? And that works out, okay? There seems to be no cases where we will end up with a carry of 1 from adding the xy digits, and also a carry of 1 by adding the qk digits, okay? It appears to be so, but, and there's a reason too, okay? By the way, there is a reason why that cannot happen, okay? And the reason why that cannot happen is because the largest digit that you can have is base minus 1. So in the base 10 situation, the largest single digit carries a value of 9. So when you add 9 and 9, okay, it's going to be twice the base minus 2. So that means, even if you had a carry of 1 from the previous column, you will be, in the worst case, adding 1 to the single digit sum from adding the digits from x and y, and as a result, that cannot give you another carry. Okay, I'm not sure whether that makes sense or not, but by the time we get to the binary stuff, it will be actually even more clear. All right, so do we have any questions about this diagram over here? I'm just looking at the text channel and see if there are any questions. All right, excellent. We got people typing. It's a good sign because if somebody is typing, that means at least one person is not falling asleep in class. And to me, that is a win. And we got 2 people typing. Woo! Okay, I'm not seeing anything yet, in the text channel, so maybe they're typing somewhere else, or they decided to delete whatever they were typing. All right, so I'm not gonna, wait for people to type, because there doesn't seem to be anyone who's posting a question. Okay, we got some people, putting feedbacks and so on. All right, cool. All right, so now we look at the sum, S of I. So S of I turns out to be pretty easy too. It is really just a single digit sum or result of adding qi and ki. Now, all of these equations here, okay, all of these definitions here, they are in the notes already. So if you're thinking, oh, man, this is boring, I read the notes and I got this part already. But good for you, okay? That's what you're supposed to have done, is to have read the notes, understood at least the definitions and so on. So when I talk about this in class, it is okay and it is right to feel a little bored, okay? Because you have read this already. So now we're going to move on to base 2. Okay, so last time we talked about how we can define the R and the C. Okay, so we found out, okay, and I'm not going to repeat the reason why we can do that because we talked about that already. So for base 2, okay, this is for base 2. The result is kind of a exclusive OR. So we can say this is X and then exclusive OR. Now exclusive OR has a symbol. Okay, it is a plus with a circle with a circle around it, but it's not a very easy symbol to write. So for the most part, I don't really use that. If you want to just spell out exclusive OR, some people spell it as XOR for X exclusive OR, and then some people spell it as EOR, the E coming from exclusive. Both I have seen, in industry and other documentations, so they're both okay, okay? But if you say, but tech, we don't have exclusive OR as an operator in C or C++, and I say, okay, fine, then we'll say, this is X and not Y, or not X and Y. Okay, that's something that we also talked about last time. And in this case, this plus here really means OR. That is Boolean. Okay. Now, what about the carry? The carry is actually very easy. The carry of X and Y as single digit in base 2 is really just X and Y. Okay, this is not X times Y, it is X and Y. Okay, so all of these operations are Boolean. That's good, right? So now we can see, oh, okay, so the Qi is easy because Qi is really just Xi exclusive OR with Yi. Sum of I is also easy because that's just Q of I exclusive OR with K of I. And then the K of I is a little bit funny, right? Because the K of I is now Xi and Yi. And then we have a plus, okay? And I'm going to emphasize that this is currently a plus, like an addition, a real addition. And we got someone who's trying to get in. SSE. Okay, it's outside of the Los Rios district. There we go. We got everybody coming in. Very nice, Omar. Very nice. Okay, to answer Jonathan's question, you can, but I'm not gonna. So when you want to write your own notes and document stuff, yes, you can use something other than the plus to denote logical OR. But in my case, if the context is clear that it is Boolean, it is going to be just a plus. Okay, because the notes is already typed up this way. And this is also how computer engineering and electrical engineering is the notation used in industry. Alright, so now we got XI, YI, and then we also have QI and KI. Okay, so now we go like, this kind of sucks. Because we got everything being done in Boolean, but now we got this plus here, okay, this actual plus that is not Boolean, okay, this is arithmetic. So now we ask the question, do we really need an arithmetic addition, or can we get away just using a logical OR? Okay, that's kind of the question. So now we want to look at a truth table, or a table. So the table goes like, okay, here's X, here's Y, and this time I'm going to use X or Y, and then we have X. Okay, to make it very clear, this is X plus Y. So we got 4 columns here. Okay, X can be false, X can be true, Y can be false, can be true, X can be, Y can be false or true when X is false, Y can be false or true when X is true, and then we look at the logical OR, right? So with the logical OR, it's pretty easy. It's going to be 0, 1, 1, 1. Okay, no big deal. And then we look at the plus. Okay, this is arithmetic addition. Okay, it's real addition. So we got 0, 1, 1, and a 2. Huh. Okay. So we look at this table, and then we say, plus or arithmetic addition gets the job done most of the time. It is only one row, the last row, that makes a difference, whether we are dealing with logical or whether we're dealing with arithmetic addition. That is the only time when they do not agree, where we have a 1 over here and we have a 2 over here. So what that means is if this row does not happen, okay, if this row doesn't happen, then we don't have to worry about anything. Okay? So now you do have to remember that this x and this y, they are not corresponding to this x and this y over here. I'm just using two symbols to basically say, okay, let's look at logical OR, let's look at arithmetic addition, and see whether we can use one instead of the other one. Okay. So now we ask the question. Okay, so the last row says, we have a 1 and a 1 over here. 1 or 1 is just 1. 1 plus 1 is 2. Okay, can that happen? So now the question is basically saying this x is really kind of referring to xi and yi. This y is really referring to qi and ki. So the question is, can xiyi and qiki both be 1s? And Omar already knows the answer is no. And he's going to explain to us why that is the case. Very good. Ki plus 1. What do you mean by I forgot ki plus 1? It is just ki. This ki, this is coming from here, which in return is coming from here. Oh, okay. Well, if the module is wrong, I will go ahead and fix it. In the equation that I wrote, that one is right. There's nothing wrong with it. Ki plus 1 is the result. Okay, so I'm looking at xi and yi. I'm looking at qi and ki, and I'm basically seeing, can xi and yi be a 1, and at the same time qi and ki being 1 as well. About the table that I wrote. Oh, okay, I see. Yep, you're correct. There we go. Thank you. Yep, so I did miss the plus 1 over there. Thank you, Omar. Alright, so now the question is, can xiyi, okay, xiyi be a 1, and at the same time qi and also be a 1? Now, we can go back and try to analyze this, okay? This is how I want you guys to solve problems like this, okay? You really kind of have to think about, okay, what can make xi and yi be a 1? Okay, so I'm going to write here, xi and yi is a 1 implies that xi is a 1 and yi is a 1 as well. That's the only time when the conjunction is a 1. Okay, what is the big deal then? Well, the big deal is qi and ki is a 1 also implies that qi is a 1 and not y, ki is a 1 as well. Okay, and what is the big deal? Well, the big deal is there is a relationship between xi, yi, and qi, because qi is defined right here. Okay, because of the way qi is defined, if we know that xi is a 1 and yi is a 1, we know qi would be a 0. Aha! Okay, so that means, if we know xiyi is a 1, it implies xi is a 1 and yi is a 1, which then implies qi is going to be a 0. Well, if qi is a 0, then we know that qi and ki cannot be a 1. So now we know that if xi and yi is a 1, we know that implies that qi, ki cannot be a 1. Now, this implication doesn't automatically mean that qi and ki being a 1 does not go back and imply that xi and yi cannot be a 1. But the other one is pretty simple too, so I'm going to open the new page here. So the other one is basically saying qi and ki is a 1. This implies qi is a 1 and ki is a 1. So now we ask, what can make qi be a 1? Alright, one more person is joining us. A little late. All right, so this is now basically implying that we got two situations. It implies I should actually just pick on this one here. Qi being a 1 implies that xi is a 0 and yi is a 1, or okay, yes, I'm mixing spelling and mathematical symbols, so I'm gonna stick with mathematical symbols this time. So and xi is a 1 and yi is a 0. Okay? But now we say, hey, but Dak, this implies, okay, this whole thing implies that xi, yi is going to be a 0. This also implies that xi, yi is a 0. So that means if you know that qi and ki is a 1, that means xi and yi cannot be a 1. So now we got the implications going both ways, which then basically is saying we cannot have xi and yi being a 1, and at the same time qi and ki being a 1. At the most, only one of them can be a 1. Alright, so after all of this logical reasoning, what does that mean? That means if I go back to this table over here, that means this row cannot happen. It cannot happen because of the restrictions. The restriction being how qi relates to xi and how it relates to yi. So xi, yi together, is used to compute qi. Okay, and that gives us the restriction that we need to basically say, nope, this row cannot happen. So if this row cannot happen, okay, I'm going to erase this row over here. So our truth table now only has 3 rows because only these 3 rows represent what can actually happen, right? And with all of these rows, we can see that, hey, 0 equals 0, 1 equals 1, 1 equals 1. So that means instead of using arithmetic addition, we can just say, logical OR would do the same trick. Okay, we do not need arithmetic addition. We just need logical OR. This is a big deal. This is a big deal because now we can finally say, and go back to this equation here, and this is just for emphasis purposes. We can finally say, yeah, we know for sure now. For this is going to be just a logical OR. We do not need arithmetic addition. Okay, so now we take a step back, okay, and we ask the question and go like, so what? Well, we can now do everything using logical operations. We can do everything using transistors now. That is the big deal. Okay, so let me turn off the tablet. Okay. So I'm doing this new thing, maybe it will work, maybe it won't work, is I'm putting the tablet under my keyboard. So this way I know that I need to turn off the tablet when when I'm done using the tablet. So we'll see whether that works out or not. Whether I'll forget sometimes that, hey, you need to turn off the tablet. So what we're doing now is we are moving on to section 5. Okay, so we have talked about section 5 already. This is basically all done using with section 5. So now the question is, can we build an adder in LogicSim at this point? Okay, and the answer is yes. Okay, the answer is yes. Depending on how you structure it, it may be a little messy, but you can certainly do it. Okay. The reason why we can quote unquote certainly do it is because now we can use logical operations to express stuff. Okay, so if you want to use exclusive OR, go ahead and use exclusive OR because we can now say qi is just xi exclusive OR. I'm going to use the symbol yi. Okay, we know that ki plus 1 is xi and yi, or Qi and Ki, and we also know that Si is Qi and Ki. Okay, and because all of these are logical operators or logical gates, we say, oh, this is cool. We can just build a circuit to do this. But somebody may look at this and say, but Tech, all you have are blah blah I equals to blah blah I, do something with blah blah I. How does this translate into an actual gate logic, right? So there's only one thing that needs to be predefined. All you need to predefine is K0 is assumed to be a 0. Okay, we just make an assumption to make everything easier in this case. Then the rest is easy, right? Because all the rest is really just to say, okay, what if I equals to 0? Okay, if I equals to 0, this is Q0 equals to X0 exclusive OR with Y0. If I is 0, then this becomes K of 1 equals to X0 and Y0, or Q0 and K0. And when I equals to 0, this is S0 equals to Q0 and K0, right? So once you're done with the first column, you move on to the next one and say, what if I equals to 1? What if I equals to 2? What if I equals to 3? And so on. So now you can build an actual circuit to perform addition. I'm very tempted to give you the actual circuit right now in Logisim, but I think I will do that if I have enough time, okay? Because I want to move on to the next topic. So with this approach, there is one problem. Okay, well, it's not a problem, but it is kind of an issue. Okay, so when we
Writing on the tablet, I don't mean to interrupt, but I
huh?
don't see anything right now
I'm
besides the.
oh okay. I'm supposed to turn on the tablet and then I forgot. Thank you, thank you. I forgot about that. All right. So the idea is to look at these relationships, right? These equations, and then we just say, okay, we'll draw a diagram when I equals to 0. We'll draw a diagram when I equals 1. Draw a diagram when I equals 2. Blah blah blah. And if you want to build a 64-bit adder, we just have to stop when I equals to 63. No big deal, right? We can definitely do this. But there's one little issue, when we do things this way. So let's find out what that issue is. Well, we can actually see the issue here, in the tablet. So the issue that we are having is the dependency of Ki plus 1 and K of I. Now, the Q terms is not a problem. Okay, the Q term is not an issue because Q of I does not depend on Q of I minus 1. If I get the Xi and if I get the Yi, I have no problem. Now, because all the bits of X and all the bits of Y are available from the very beginning of the entire thing, so that means I can simultaneously compute all of the Q terms using a multi-bit gate in Logisim. Okay, all of those things can happen in parallel, and I can get all 64 Q bits computed at the same time. Okay, which is great. Assuming that I have the Q bits and the K bits already, I can compute all of the sum bits at the same time too, because the sum bits amongst themselves have no interdependency. They only depend on the Q and the K bits. So that means once I have all the Q bits and all the K bits, I can simultaneously compute all of the sum bits at exactly the same time. So it's not a bottleneck. The bottleneck is over here, because Ki plus 1 depends on K of I. So that dependency means I can only reliably compute the actual value of K1 once I know what K0 is. But I can only compute K of 2 when K of 1 has settled down. I can only compute K of 3 when K of 2 has settled down, and so on. So that means now we have a linear dependency of all the carry bits, and which also means the actual amount of time to do the computation is linear to the width of the numbers that we are adding. Okay, I'll give you a rough estimate. Okay, this is probably off by 1, but I'll just use it as an example. if we know that a 1-bit adder is going to take 1 nanosecond, then a 64-bit adder would take 64 nanoseconds. Okay, because it's linear, because we have a linear dependency of ki plus 1 depending on k of I. So you look at this and go like, is this really an issue? I mean, well, it is not an issue if your competitor cannot do this faster. Okay, so think about Intel and think about AMD. Okay, if Intel says, hey, this linear dependency is okay, 64 nanoseconds is no big deal, we'll just do it this way because it just looks clean, it's easy to work with. Okay, and then if someone from AMD took my class and they say, but Tech says there's a faster way to do this, it's called carry look ahead, and then AMD decides to go ahead and use carry look ahead, and it's a whole lot faster, okay, compared to what we call repo carry repo, which is the linear dependency thing. Then Intel has a problem, right? Because your competitor AMD can do the same thing with almost just constant time. Okay, the width of the operation has nothing to do with how much time it takes. Then it becomes an issue for Intel, right? Because then Intel will have to take my class also to learn what is carry look ahead. So is that okay? Does everybody kind of get the idea of why what we have at this point, even though it works, it doesn't work efficiently? There's a better way to do this. And Andrew is absolutely correct in the text channel. This is exactly why we have the carry look ahead mechanism. Cool. So what we have at this point is we are done with section 5. Okay, so we're done with section 5. I'm going to go back to the notes, and when I do that, I need to get the tablet out of the way, both physically and also on my keyboard. So I'm going to take it out of the way. So we are done with section 5, and now we're moving on to section 6. So section 6, if you look at it, most people look at section 6 and go like, oh, okay, this is just a little bit of extra stuff. No, this is actually the important stuff in this module. Okay, I mean, just think about it this way. Okay, if you watch an infomercial, and you just watch the first portion of how the product how the product works and how much money they want from you, you'll be a sucker to pay that much money, because the host is going to say, but wait, there's more. And they're going to say, if you buy 2, you can buy 2 with the price of just 1 and a little bit more. If you buy 3, we'll even waive your shipping and handling fee, blah, 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 right? So, but wait, there's more signifies that something really important is coming. Yeah, I know, this is the infomercial culture thing, but, I just borrowed that. Alright, so what we'll do now is to get on to section 6. And section 6 starts with the description of the problem, the linear dependency of ki plus 1, on k of I. And then it suddenly segues to something that is really messy, which is this derivation here. I do not expect people in this class to be able to do the derivation itself, but to understand the derivation, I think it is reasonable. If you have not taken CISP 440, this will help you with CISP 440. If you have taken CISP 440, this is sort of a review of some of the stuff that you learned in CISP 440. But either way, I think it is helpful. Okay, so we'll just go ahead and quickly go over these lines of derivation. Alright, so the first line says, k of I plus 1 equals to blah, blah, blah. That's just definition, okay? We know this definition from way before this, okay? From the first line to the second line, I just expanded, what C is representing as a function. And in base 2, this works out, okay? In base 2, XI is XI and YI, QI is XQI and KI, and then the plus is a OR. Okay, so on row 2 we have Boolean operations already. And then on row 3, we expand the definition of QI. So QI always expands to the result, the single digit result of adding XI, YI. And then from here to here, I expand the R function, for the case of base 2. This is just a long way of writing exclusive OR, but it works too. And then from here to here, I use distribution in Boolean algebra. So I know some people took CISP310 from me last semester, so you should still remember this stuff. Okay, this is just distribution. And then from here to here, we have the identity rule by introducing this extra 1 over here. It sort of works in normal algebra too, because anything is the same as anything times 1. Okay, so as it turns out, true is also the identity with respect to conjunction in Boolean algebra. And then from here to here, it starts to look kind of awkward if you are not exposed to Boolean algebra, because in Boolean algebra, true is the same thing as true or something. Well, that's because true or whatever is always true. It doesn't matter what k of I is. K of I can be true, k of I can be false. It doesn't really matter, because when we are talking about true or ki, it's always just true. Okay, so I just introduced this term over here, which then I use to expand. Okay, so XIYI times 1 is here, XIYI and KI is over here. I said times, but I meant and. And then from here to here, I duplicated a term. Okay, because in the previous one I got 4 terms, and now I got 5 terms. And the one that got duplicated is this term over here. Okay, you can see how XI and YI and KI only has 1 occurrence over here, but now it has 2 occurrences. 1 occurrence over here, and the other occurrence, over here. In Boolean algebra, this is perfectly okay. Okay, if you have a variable A, okay, and you look at the variable A or variable A itself, that doesn't really change anything, right? Because anything or anything is just that anything to begin with. So we can always clone items either in an AND or. Okay, it doesn't really change the value of the entire expression. And then from here to here, I use I think this is called association, because it doesn't really matter when you group a whole bunch of items that are ORed together, how you put the parentheses. So I just explicitly put parentheses around these 2 items and put parentheses explicitly around these 2 items. And then from here to here, I use factoring, which is the reverse of distribution, and the same thing over here. And then from here to here, I use simplification, because yi or not yi is always true, because one of them is going to be a 1, and since both of them are inside a OR, that means the result of an OR is guaranteed to be a 1. And the same thing over here, we got xi or not xi, so one of these 2 terms in the OR has got to be a 1, and as a result, the OR is going to be a 1. And then from here to here, I just took the true out, because it is just the identity of conjunction, and we don't need to write it here. Okay, it's not wrong, it just doesn't need to be here. And then from here to here, I use factoring again, because both of these 2 terms have a ki in it. So I just factor out the ki on the outside, and then I say, okay, the whatever is left is the xi from here, it's just the yi from here, and then we just make a new OR out of those 2, and now we have the final form. Lots of Boolean algebra stuff going on, okay, but it's just really mechanical stuff. So what is the big deal? Because somebody, smart is going to say, but Tak, you haven't really solved the problem, because this is ki plus 1 and it still depends on k of I. This sucks. We go through a lot of mechanical manipulation in Boolean algebra and we did not solve the problem. Well, then we have a paragraph that looks like this. It looks completely insignificant, okay? But trust me, people always ask me, How is G defined? How's P defined? It is over here. G is defined as GI is XI and YI. PI is defined as XI or YI. This is the only place where G and P are defined. But they are really important. You ask, why are they important? Well, because now we can rewrite Ki plus 1 to be G of I or P of I and K of I. Because G of I is, by definition, X of I and Y of I, and then P of I is, by definition, X of I or Y of I. Then you go like, but Tech, you still haven't solved the problem. The problem of X of I, K of I plus 1 depending on K of I. You still haven't solved that problem. You have made it look simpler. There are fewer symbols involved, but it is still the same problem. Okay, but that part is true. But now we see what we can do next, right? So what we do next is to say, well, we'll go ahead and say, what if I is 0? Okay, if I is 0, then we end up with K of I or K of 1, because on the left hand side we have I plus 1, right? So if we have I plus 1 and I is 0, then we have K of 1. So now we have K of 1 being G of 0 or P of 0 and K of 0. And by the way, the usual rules of operator priority still applies. So the OR has a lower priority compared to the AND, so the AND is computed first. Okay, I was kind of assuming that people know this from algebra, but I want to kind of say explicitly that we still have those rules in place. Okay, so conjunction always takes place first, and then we deal with the disjunctions. Okay, so this is no big deal. And then what do we have? So next we say, what if I equals to 1? Okay, when I equals to 1, then 1 plus 1 is 2, so we have K of 2 on the left hand side. And then we have G of 1 or P of 1, K of 1, and then somebody's going to say, okay, Tech, we got the same problem. We have a linear dependency. And then I go like, wait, but hold on a second here. We know what K of 1 is. K of 1 is G of 0 or P of 0 and K of 0. So we expand, okay? This is the trick, okay? This is the trick of solving the problem that we have. We expand it, okay? So we expand K of 1 to become G of 0 or P of 0 and K of 0, and then we expand this, okay? We use distribution to quote-unquote expand it. So we end up with K of 2 being G of 1 and P1 and G0, or P1, P0, and K0. Then you go like, okay, it still looks kind of complicated, especially when you compare that to K of 1. I mean, K of 1 is easier, K of 2 is harder, and then if we reapply the same technique, K of 3 is even worse. Then you go like, what problem have we solved? I have solved the original problem. The original problem was K of I plus 1 depends on K of I. That dependency is gone. K of 2, if you look at the last expanded form, K of 2 does not depend on K of 1 anymore. It only depends on K of 0 and a whole bunch of P and Q terms. K of 3, yeah, we got more P and G terms over here, but in terms of K terms, it also only depends on K of 0. So if you apply this reasoning, just kind of expand it out a little bit, just not to even physically write it out, okay? If you just mentally expand what we are doing, then you can say, okay, well, K of 4 is going to be a longer and more complex expression. It will have a lot of P's and G's in it, but it will only have K0 in it. It doesn't depend on K of 1, K of 2, or K of 3. Okay, so you can kind of expand this approach and go like, okay, so that means all the K terms really boil down to a whole bunch of G terms, a whole bunch of P terms, but when it comes down to K terms, they only depend on K0. Okay, then what about the amount of time to do this? Because remember, the whole idea is the linear dependency of K of I plus 1 depending on K of I is making things really slow because it has a linear dependency. We have no linear dependency anymore. But someone is going to say, but we have a longer and more complex expression. Doesn't that take longer? And I'm going to say, no, it does not take longer. And then someone's going to say, but wait, hold on a second here. It will take me longer to evaluate that expression, the expression of k of 3 compared to the expression of k of 1. What do you mean by it doesn't take longer? Well, that's because you don't have logic gates in your head. We don't, okay? Which is a problem sometimes, and it is a nice thing sometimes. But we don't have logic gates. So now we take a look at from the logic gate perspective, okay? So what we'll do is I'm going back to the tablet. I'm going to write the equation first, and then I'll switch the screen to the tablet because I need to write this out first so that I don't forget. Okay, so I'm going to just write down k of 3 is g of 2 or p2g1. So from here on, I'm not even going to use and. I'm just going to say p2p1g0 or p2 p1 p0k0. Okay, so now we are ready to transition over. And Andy is correct. So getting back to the text channel, Andy is correct. The p and the g terms only depend on the x and the y terms. They do not depend on, there's no linear dependency when we need to compute the p and the g terms. So they can all be done, with parallel gates. Once x and y are known, it will only take a constant time to figure out all the p and the g terms. Okay. And then Nicholas is asking, so as long as any one of those terms resolve to true, k of I is resolved within a fixed amount of time. Okay, that's basically the bottom line. Okay, so now I make a claim. I make the claim that no matter which k of I we are trying to solve, it will take constant time to solve that particular k, and there's no interdependency. Once we know x, y, and k0, it will take constant time to figure out a particular k term. That is my claim. Alright, so we got touchpad screen. Okay, so we are switching over. And then Chris has a equation typed up here. Yes, that is correct. Alright, so now we will say, what about this expression here? Doesn't this take a lot of time? Okay, so we'll go ahead and figure out how to do this. This is going to look very messy. Don't worry about it because you're going to make this circuit too. But I'm just going to make this here. Okay, this is not even in a circuit way. x0, x1, x2. Oops. I say one thing, I type something else because I was already thinking about y0, y1, y2, and then we get a k0 standing out. So these are the things that we are given with. In other words, at clock 0, at nanosecond 0, these are the things that we are given with. So now what we need to know is how do we figure out k of 3? Okay, we just want to figure out k of 3 specifically. Okay, so quite obviously the first thing we need to do is to figure out all the p and the g terms, right? So now we say here's g of 0. So g of 0 is an AND gate that has x0 and y0 going into it. We have g of 1. We got x1 into one of the input pins, and then y1 going into the other input pin. We got g of 2. Is it okay for me not to draw g2 because I think most of you kind of get the idea? Okay. All right, so I'm not gonna draw a whole lot of stuff, but I do want to draw one of the P gates. Okay, so I'm just gonna draw P1. Okay, so P of 1 is coming out of an OR gate. Okay, just looks different, right? But it is still only coming from X1. Okay, so X1 here goes to here, and then Y1 goes from here to here. And then we can also compute P2, kind of the same thing. It just needs one input coming from X2, the other one coming from Y2. So here's the question. Can all the G terms and all the P terms be computed in parallel at the same time? Yes, right? They can all be happening at exactly the same time because they are different gates. Okay, so that means if I want to measure propagation time, so propagation time is basically the amount of time to go from here to here. Because transistors do not work quote unquote simultaneously, so when the input or when the gate of a transistor changes state, it takes a little bit of time for the transistor to turn on or turn off the valve. Okay, so that time is intrinsic to it mostly depends on the capacitance of the gate of a transistor, but it also depends on many other things. So if you are in electrical engineering or in physics, then you know that there's something called resistance. Everything has a little bit of resistance, and everything has a little bit of inductance as well. So when you look at inductance, resistance, and also capacitance, all of those things contribute to propagational delay and lag time and stuff like that. And so that means, once we know all the x, y, and k0, it takes a little bit of time to get to all the p and the g terms. Okay, so we call it one. In this class, I just call this one gate propagational delay. Okay, that's just one single delay. All right, so then what do? We look at the equation and go like, g of 2 can be by itself to contribute to the overall OR, so that's not an issue. But we look at this term here and go like, hey, this one depends on P2 G1. Okay, so we look at this term and go like, okay, we need a G1 and P2, and I need those two to be going to an AND gate. Then we look at this term, go like, this one also needs P2. Okay, it needs P1. Okay, so we need P1, and it needs G0. Okay, so we take G0, and then we make another AND gate over here. And then we look at this term over here. It needs P2 again. All right, so P2 is really popular. Okay, so we take this one, and it needs P1. Okay, P1 is kind of popular. And then P0. This is the first time and only time we use P0. And it also needs K0, which was available all the way from the beginning. So we use another AND gate. All right. So now we look at this and go like, we got one AND gate that only has 2 inputs. We got another one that has 3 inputs, and we have another one that has 4 inputs. So the idea is you can design transistors, to implement these gates, and they take the same amount of time. Okay, so even though one has 4 inputs, it will only take the same amount of time as the other one that only has 2 inputs. Okay, so the amount of time to go from here to here is also just one gate propagational delay. So now we have 2 together, all the way from, when we get the x, y, and the k terms, all the way from here to all the way over here, we now have 2 gate propagational delays. So at this point, we have the G2, we have the P2 G1, we have the P2 P1 G0, and then we have the P2 P1 P0 K0. We got all of these items already, so that means we take G2. Okay, we take the output of this AND gate, we take the output of this AND gate, we take the output of this AND gate, and we feed all of these into a OR gate. Okay, so we got this one here, this one over here, this one over here, and this one over here. And when this OR gate is done, which would be the third gate propagational delay in our case, then we have K of 3 ready. So it takes 3 gate propagational delays to get from the input pins, X, Y, and K0 are the input pins, all the way to K of 3. Then you go like, okay, what is the big deal of K of 3? Well, we need K of 3 and Q of 3 to compute S of 3. That's why we need K of 3, okay? The qubits are not the problem. The qubits are available pretty early on because you just kind of think about the qubits, right? So Q of 1, just takes, I X of 1, and it takes Y of 1, and we have to get them through the exclusive OR gate, and I can't even remember what it looks like, so I'm gonna look it up. Excuse me. So exclusive OR gate symbol, and it looks like a OR gate with a bar in front of it. Okay, so we draw that over here. Okay, but you can get the idea, right? You get the idea of all the qubits. They're available pretty early on. Okay, so we got Q0, Q1, Q2, Q3, blah blah blah, and then we just take this. Once we have the K3, we take the Q3, right? We take these two, and we say, let's go through another exclusive OR gate. This now becomes S3. Okay, so let me see if you guys have any questions about the diagram that is illustrating how we get K3, and once we get K3, what do we use K3 for? Okay, so by the time we get to S3, we would have 4 propagational delay because we need that one extra exclusive OR to combine K of 3 with Q of 3. Now Q of 3 was computed 2 propagational delays ago, but I can't do anything with it until I have K3 also being computed. Alright, so I'm reading the text channel. What do each of those lines represent at the top of the diagram? So each one is a delay. So this is one point of delay, this is another point of delay, this is the last point of delay. So this is where we start, okay? This is time 0. This is 1 propagational delay, this is 2 propagational delay, this is 3 propagational delay from the time when the input pins are present, or when we have the correct zeros and ones at the input pins. Alright, we got some more questions coming, and I'm gonna wait a little bit here. Okay, so that's good. That's good. You do not, well, if you don't have X3 and Y3, you don't have a Q3. If you don't have X3 and Y3, that means you only got 2, at the most 3 inputs, or you're adding things that are only 3 bit wide. X3 and Y3 implies that you have 4 bits. Because we count from 0. Alright. Oh, I take it back. So I did make a mistake, sorry. I made a mistake here. Good thing the tablet has a eraser feature. That takes Q of 2, not Q of 3. I made that mistake. Okay. It's good to ask questions to question what I have just written, because sometimes I make mistakes. And also, since I made that mistake, no, actually I take it back. I did not make a mistake here, because this line is not a mistake. This is actually correct, because this is K3, and K3 is only going to be used in conjunction with Q3, and Q3 depends on X x3 and y3, which is not illustrated here. So if I were to write x3 and y3 over here, whoops, I say one thing and I said one thing and then I wrote something else. But x3 and y3 are not used to compute k of 3, but they are used to compute q of 3, which then is used to combine with k3 to figure out what is s3. Is that okay? Alright, cool. So now the question is, if we are trying to figure out K2, which is a simpler case, can we get away with fewer propagational delays? That's kind of the question. If I want to work with K of 4, which is going to be a more complex design, but in terms of how many propagational delays we're talking about, would that be the same or would it be more than K of 3? So I kind of want you guys to think about that a little bit. I'm reading the questions. I'm not really quite sure what S3 can be OR gate. No. Why can it be an OR gate? How is the S bits computed? That's the question. How are the S bits computed? It's in the notes. It's also on the tablet earlier. So let me just kind of go to the previous page, or the one. No, just one's fine. The S bits are. Oh, okay. I did make a mistake here. Okay, I stand corrected. I did make a mistake. This is QI exclusive OR with KI. There we go. So it is not an OR gate. It is an exclusive OR gate, Luke. All right. And this has to do with an earlier discussion of SI is really the R of the Q and the K bits. That's why we have an exclusive OR. It is not a conjunction. It is supposed to be an exclusive OR. All right. So I'm gonna wait a little bit until all the questions are cleared. And I'm looking at the time. Yeah, we got plenty of time. Because the lecture ends at 6:50, and we still have a little bit of time to go over the rest of the module. There's only a little bit left. Alright, so here comes the questions. Alright, so Marco asked, when building the look-ahead carry adder, do you still use the full adder from that? The answer is no. It's the carry look-ahead mechanism is a different mechanism. We do not use the full adder from carry ripple adder. And then Keaton asked, is K64 the norm or question mark? Well, that's just the case if you have a 64-bit adder like most modern processors. Most modern processors are 64-bit processors because the width of the adder is 64-bit wide. And then Andrew commented and said, I'm currently messing around with Wikipedia's carry look-ahead unit design. Cool. But guess what? That's our homework for tonight's lab. Well, I mean, it's half of it, but this lab is broken up into 2 halves. So we do half of it tonight. Make sure that you save the file, and then the other half would be on Thursday. So, and then the next question is, so far you have a 60-bit adder working. A 60-bit adder is a killer already. If you think about the carry look ahead mechanism, the equation for K16 is messy. You're gonna have like 16 gates in the just to compute K16, and then you need the gates to have 16 inputs, which I don't think you can do in Logisim. So that one is going to be quite messy if you want the entire thing to make use of the carry look ahead mechanism. Alright, so we still got Michael and Andrew typing, so I'm gonna wait a little bit before we kind of switch back to the module to finish it up. Alright, so Marco made a 4-bit carry look ahead. Yeah, well, the 4th bit is really not too bad. It's really just a little bit worse than the K3, but you need, yeah, so it's not too bad. Alright, so we still got more typing going on. And I'm just going to wait a little bit. But okay, gotcha. But the idea is, as long as we can afford to have AND gates and OR gates with any number of inputs, okay? And we don't really care about, how many gates we use. The amount of time does not change. Okay, when we want to know how much time it takes to compute k of I, it's always going to be 1, 2, 3 propagational delays. Okay, that really is the whole point of carry look ahead. Now, in reality, do we have AND gates that can have 64-bit inputs? The answer is, well, probably not. Okay. But that means the AND gate can be, so let's just say the fan in ratio is only 8:1. In other words, the the maximum number of inputs into one single AND gate is only 8 inputs in order to compute an output. So that means if you have 64 bits, then you need 2 tiers of AND gates to compute the AND of the 64 bits. Because bit 0 to bit 7 will go to the first AND gate, bit 8 to 15 will be going to the second AND gate, and so on. So now you have 8 AND gates, each one taking care of 8 inputs. And then each one of the AND gate, the output of each of those would go to a secondary AND gate. So you will basically be looking at the log of the number of bits that you're dealing with. But log of n is still a whole lot better compared to just n. So in reality, the actual amount of time is likely to be log of the width of or the number of bits that we are adding, or the width of the adder. But that is pretty close to a constant time. Okay, it is a little less than constant time, but it's not that big of a deal. So even if you take into consideration of realistic stuff but we cannot have super AND gate that has 128 bits as the input, fine, break it up. You'll still be a whole lot better compared to carry ripple adder. Okay, that's just completely linear. Cool. So now we're gonna switch back to the notes. Let me turn off the tablet and then go back to our module for today, which is not this one. I think it's this one. There we go. So now we have this to understand. Okay, so what exactly is that thing? So when you see the big V symbol, this is a big OR. Kind of look at it as a sigma. Okay, when you look at this big, kind of inverted V symbol, is a big AND. So both of these are really just loops. Okay, and so is this one here. I is the index of the loop, so I goes from 0 to n, and that affects this portion here. So you can see how this AND here is using the index I, because the index j starts with index I plus 1, and it goes all the way to n. So this is really just a way to generate these expressions. In other words, if you tell me what n you want to work with in order to compute k of n plus 1, I can give you this, which then can be turned into just a bunch of loops, right? To actually generate this equation over here. So let me take a look at the time. We got about 8 minutes left. Okay, so with 8 minutes left here, I think I got enough time to kind of illustrate what this means. Okay, so I will go ahead and let me think. Let me think. I can. I think I can do this using JavaScript. Okay, so let's see how rusty my JavaScript is. Alright, so we'll go ahead and do a carry look at head adder caa.js. Alright, so we'll go ahead and do the loop stuff. Okay, so we'll say use strict and I think it needs to be quoted. I cannot remember which way. Details. Okay, I think it's just that. Okay, let me just check. Node ca.js. Okay, that it likes. Okay. Not sure whether it's actually effective or not. I guess I will find out soon enough. Alright, so now we just write a bunch of loops. Okay, we say, let me just look at the equation at the same time, and then we look at the code. Okay, so we move this up a little bit. Actually, what I want to do is to move this all the way to the top of what you can see. This is as far as I can go. And then put this under, so this way we can look at the loop and look at the code at the same time. And expand this portion here. Alright, so now we'll say let I, and we have to first determine what n is. So we say const n equals to, okay, what do you want me to use n as? Let's make n equal to 2. This way we can double check whether our k3 is done correctly. So this I goes from 0, I is less than or equal to n, and then plus I. Of course, I forgot that this needs a semicolon. There we go. This is a loop. And we also need an array. So we'll say let or terms equals to an empty array. Okay. So now we need to figure out the AND terms. Okay, so for each one we say and for let AND terms, and this one we can start with a g of I. So we say g of I. So we say g I is over here. Okay, there we go. And it's also an array. So this is just the first term in the entire array. So now we have a double loop. So the inner loop deals with j as an index. So this inner loop here is corresponding to this AND operation here, the gigantic AND operation, where j starts with I plus 1, j ends, j is less than or equal to n is the stay in loop condition, because we want j to equal to n in the last iteration. And this is supposed to be plus I as a post operation. And then we have a plus j as a post operation here. So now we're dealing with each term inside the big AND operation, which is p of j. So now we say AND terms push. So we are just adding an item to the array called AND terms. And the item we are pushing is going to be p of j. So it's p j like so. Okay. So when we are done with this inner big conjunction, then we have to AND this. Oh, this is already done, because I pushed all the items already. So the term that we are adding to the OR term over here is going to be just one big long conjunction. So we can use join, okay, to do this operation. So we can now say, okay, wrong terminal. So now we can say or terms push. It would be and terms dot join, and we don't need anything to actually join them, so we can just give it an empty string like so. So when this is all done, then we would have this gigantic OR term, okay, but we have another kind of smaller term to OR that with. So this is the other term that we need to work with. So now we say let and terms equals 2. We know k0 has to be there, so now we know that we have at least k0 in here. And then we have another for loop. Let I equals to 0, I is less than or equal to n plus plus I. And then for each iteration, we have p of I, as a part of this AND operation. So now we say AND terms dot push backtick. It would be p of I, like so. So when the loop is done, we would have this gigantic end term. So and then that needs to be ORed with the gigantic OR term. So now we say OR terms dot, we forgot. The syntax is off a little bit because I forgot. Okay, I see why. Because I use a close square bracket instead of a close brace over here. So now we push the AND terms dot join by nothing. There we go. And then the last thing is we can do a console.log of OR terms dot join, and this time we need the plus symbol because this is one gigantic OR, like so. And I think that should do it. Okay, there's a whole bunch of text going on in the text channel when I was writing the code. JavaScript does not need to use semicolon. That is correct. It should. Well, there are different people saying, different things. Some people say that yes, it should because I come from C and C and C++. The semicolon is always there. And let me tell you, it's good to get used to not using a semicolon to end something. I got bitten by that one, several times, especially when I want to return something that spans across multiple lines. But that's a topic for a different day. Okay, so I'm gonna try this one. Let's say, okay, so the question is that correct or not? So we'll check, right? Okay, so we got K3 over here, and there we go. Alright, so we got G2 on its own. Okay, that's good. P2 G1, P2 P1 G0, and then P2 P1 P0 K0. So the things are not ordered exactly the same, but it does work. Okay, it does work. So I want to show you this because this is kind of how okay, let me go back to here. So this notation here is implemented by this code over here. White space as syntax is bad for accessibility. That means Python is not very good, doesn't it, Caleb? 64? Sure. Let's work with 63 bits, which means n equals to 63. Okay, so we're computing K64, by the way. All right. So are we ready? I mean, it just looks ugly, but there's regularity in it. So it just looks ugly because the longest conjunction has 65 items in it. Oh, I take it back. 64 items. 64 or 65? 65 items. I take it back. 65 items because we got the K0 and then we have the 64 p terms in it. So the largest conjunction has 65 items, and then the OR also has 65 items in it. So that's why it just looks awful. But okay, if you look at the code that generates that, it doesn't look nasty at all, right? I mean, we just got a double loop. We got some push into an array, then we got some join operations, and we are done. This is why it is so cool to be able to specify logic, or the structure of logic using something that looks like a programming language. And this is also why, and I'm pretty sure some of you plan to transfer to Berkeley. So at Berkeley, they have a computer architecture class where you're supposed to design something that is a little bit more usable compared to my toy processor. And in that process, you have to use an HDL, a hardware description language. So there are two HDLs used by industry, and I think Berkeley uses Verilog, but I could be wrong. So one is called Verilog, the other one is called Vhdl. And if you look up these two terms, they will basically, they're slightly different in terms of syntax, and I haven't used either one. Okay, so don't ask me about specific details, but that's what they are. Okay, these two are specialized languages to generate a description of what goes into a processor. So if you become a processor architect, okay, you'll be writing code not in JavaScript. Okay, JavaScript is sometimes an awful language, a god awful language for certain things, but you'll be writing something to the effect of what I have just written in order to specify how gates relate to each other inside a processor. And the language that you'll be using to make that happen is either VHDL or Verilog. I think Verilog is more C-like, which means it is not nearly as well thought out as a language, but because it is very pragmatic, people use it. And then VHDL, if I remember correctly, is a language that was specifically designed for this purpose, but it is harder to learn. It's kind of like Ada versus C in regular programming. VHDL is similar to Ada, sort of well planned out, has got lots of features. A gigantic committee came up with it. And then Verilog is kind of like C. It came up because people needed it right away. It was used for a purpose that it was not exactly designing logic. I mean, Verilog was originally used for verification. Okay, that's where the veri is coming from. So it was originally used for verification, but people expanded the use of it to also to be useful for describing gate structure, or just the internal structure inside a processor, or stuff like that. Look at these as non-graphical ways of doing things compared to Logic Sim. All right, and we got some stuff going on in the text channel. Okay, so I can see you guys are having fun. That's good. And Omar says, he has a friend who uses Verilog at Intel. I would not be surprised, because Verilog is it's just a very pragmatic language. It's not the best, it is not super well thought out, but it's used a lot in industry, just like C. C is not really a well thought out language, but it's very pragmatic, it's useful, and a lot of people use it. They also use it for verification, so it could be either one. In terms of Verilog, it could be used only for verification, but it can also be used in order to design the internals inside the processor. Yep. And we are over by 6 minutes, and Jonathan is typing. I'm just going to wait a little bit while I open up today's lab. So let me go to today's module. Alright, so yes, so we do have a homework. This is part 1 of Carry Look Ahead Adder. So let's open it up. Oh, okay, that's good. I was responding to Jonathan's text, and because everything is timestamped, so if people are just watching the video, they can go back to the text channel and basically understand what I was responding to. Okay, so first thing first, the access code is 3x3 part 1. So I'll just copy that over here. 3x3 part 1. And it's a slightly longer lab, but it should be quite doable by tonight. So I'll give you guys up to 10:50 p.m. tonight to do this. And this one does require Logisim, so you gotta use Logisim to do it. And then we save and publish, and there we go. Alright, so any further questions before I stop my streaming? And I'm not even going to check the off-topic stuff. Okay. Oh, okay, that's an interesting question. What is a well thought out programming language, in my opinion? Rust is not bad. It depends on whether people use that programming language for what it is designed to do. If you are limiting to the context of using a programming language for what it was designed to do, this is going to date me, okay? Because the two languages that I think were well designed were these two, Prolog and Lisp. They were the AI languages back in the past. Yes, Lisp. It's list processing. That's why it's called Lisp. And then Prolog is a programming language. Well, some people don't even recognize it as a programming language, but Prolog was a language designed to handle predicate calculus. So you can actually enter, I guess, statements in predicate calculus, and it is an engine to evaluate those things, and it can figure out things too. It can quote unquote solve problems once it understands the rules. Not always quickly, but it can get the job done. So these two are kind of interesting languages. Because I don't think about whether a programming language is well thought out or not. I just use the one that works. Oh, okay. So to answer Chris's question, or to comment on what Chris is mentioning, COBOL is having a comeback. I have been spending the last 2 semesters, this is the 3rd semester going, to create programs and courses using COBOL and JCL and Rex and other things that IBM mainframe computer use. Because the state agencies, Wells Fargo, American Express, and many other huge institutions are running out of people who can program in COBOL and JCL and Rex and all the other things that mainframe computer use, and they cannot transition. There's no plan, and some have tried many times and could not transition to newer programming languages. So they are all going to stick with COBOL in the foreseeable future. Yeah, Nathan, your dad probably, if he still wants to work, he has no trouble finding work as a consultant. There are tons of companies out there, needing people who can program in COBOL. Yep, he's retired, but he can go back to work if he wants to. Okay, to answer Jonathan's question, it's mostly the risk. The transitional risk is huge. So because you're not talking about an app that you're running on Android, and what the app is doing is to keep track of your yoga exercise. Okay, because if that app goes bad, okay, if there's an error, big deal, right? It just doesn't track your yoga exercise correctly. You're talking about things that will print out social security checks, things that will calculate franchise tax for corporations and stuff like that, or things that will basically be working off with banks, to calculate interests, to issue out checks to people, when there's dividend from your stock and so on and so forth. So they cannot really afford to change all the programs from one programming language to another programming language. The risk involved is just way too much. And then the other thing that's interesting about COBOL is it is actually a surprisingly efficient programming language. Optimization, code optimization in COBOL is actually very, very easy. And that has to do with COBOL is being a very verbose programming language. There's usually like 20 different ways of doing the same thing. And out of those 20 ways, one is usually recommended because it is the most optimal way to do something. So optimization in COBOL programming is actually surprisingly good. Let's see, where is it here? No, you can learn COBOL on the job. You can also pay to learn it. But once ARC starts to have our mainframe programs, then you can just take classes here. It might take another year or two even to actually start to offer classes like that. But once we do, there will be those students would not have problems finding jobs. Yeah, COBOL is an easy language from the perspective of it doesn't really have a whole lot of tricky stuff like in JavaScript, if you want to use anonymous functions and there are a lot of tricky things you can do in JavaScript, none in COBOL. Yep, COBOL. In fact, the difficult part of learning COBOL is you know how to do something in a very elegant way in Java, in JavaScript, in Python, and most modern programming languages, and then you go to COBOL and go like, okay, I bet you it has a way to do this the same way that I do in those other programming languages, and then the answer is no, we don't. Then you go like, but then how do we do blah blah blah? Like virtual abstract classes, pure super classes, and you just don't. Okay, you just have to kind of do it the dirty way in some cases. Yes, that was the whole idea of COBOL. Is it is supposed to be readable for business people. If you just download a sample COBOL program and just read it out, it reads like a story. Try the same thing in JavaScript, or worse yet, Python. And then EDD took a dozen people with zero experience and hired a vendor. Yeah, I don't know how well that works out. Because right now I am developing curricula, basically classes that goes along with an apprenticeship program that the state has. There we go. And that's also in VS Code. So COBOL has a kind of modernized front end. You can download an extension in VS Code and actually be able to COBOL and program in COBOL and also communicate with a mainframe computer to run the job. Yes, it does kind of make it look nice, but from my perspective, you're basically having a new paint job on a biplane when everybody else has jet engines. It's but the biplane is still needed because in order to dust crop, okay, in the field, you cannot you cannot use a jet to do the same thing. You have to have a slow flying, airplane that's easy to maintain and inexpensive. Yeah, it is. It's kind of like that. It's kind of like putting the paint job and the stripes of a Blue Angel on a biplane that's doing crop dusting. But it's a great job. I mean, it's great job security, and all the employers who are looking for COBOL experience, typically have like excellent plans in terms of health coverage, and with the state, even though it's not as good as before, the retirement plan is still pretty good. So there is that. All right, so we got some. So I think it's okay for me to turn off the streaming because I think most of the stuff going on is now in the text channel. So I'm going to turn off my voice and video streaming at this point. So